Good afternoon, everybody. I'm Paul Mathews. I am the porter for Group 3 on the air conditioner experiment. To give you a quick review of the background for this experiment, we're dealing with the ideal vapor compression refrigeration cycle. Basically, we start with a refrigerant as a saturated vapor, passes through compressors, superheated to a superheated vapor state, goes through a condenser, drops back to a saturated liquid, which then throttles through an expansion valve and changes to a liquid vapor mixture, and then across the evaporator goes back into a saturated vapor and then repeats the cycle. Now, as far as what we expect to see with our temperature entropy and pressure entropy diagrams, it should look like this for the temperature entropy. As we go to the, as we start off, we have as we go across the compressor, we increase our temperature dramatically up to state 2, then temperature drops back down and go across the condenser. First we hit this, instead of going straight to a saturated liquid, we hit the saturated vapor state right there. Then as we release heat, we get to a saturated liquid. We go through the expansion valve, back down, we decrease our temperature, and across the evaporator as heat's added to the refrigerant, we get back to the saturated vapor state. As far as the pressure enthalpy, again starting before the compressor, as we go through the compressor, we have an increase in enthalpy and pressure. Going through the condenser, we have isobaric process, our enthalpy is going to decrease. Across the expansion valve, our pressure is going to decrease at constant enthalpy, and then going back through the evaporator, we're going to increase our enthalpy again at constant pressure. Now, as far as what we actually saw, for 3 different charge states, that's different amounts of freon in our system, we collected basically temperature and pressure readings at each of these 4 locations. The temperature and pressure is then used along with property tables to find the enthalpy and entropy that went along with those temperatures and pressures. I was able to develop these diagrams. Now, here first our temperature entropy diagram looks pretty much as expected, except for this initial temperature before the compressor was high. I think that actually was recording ambient temperature as opposed to actually the temperature of freon. That's the only explanation I can think of for that. But other than that, we pretty much see that general pattern demonstrated here. This was not actually a recorded point, but I added that so that it would have the shape. This is where, again, as I said, as we go through the condenser, we're going to first hit that saturated vapor state, then go back across to the saturated liquid state. Now, the pressure enthalpy, again, looks very much like expected across all different charges. The trends we did see is just as the charge decreased, so as the freon in the system decreased, we saw a slight decrease in temperature across the board and a slight decrease in pressure across the board. That's pretty much what I would expect to see. Coefficient of performance is calculated as the enthalpy change for the refrigerant across the evaporator divided by the enthalpy change across the compressor. In here, as you see, as you decrease the charge, so you decrease the amount of freon in the system, we see a decrease in the coefficient of performance. That, again, should be expected because you have less coolant. Other information we took in addition to the freon measurements, we recorded the wet and dry bulb temperature for the air entering and exiting the evaporator. What this did for us was allow us to calculate the enthalpies of the air as it entered and exited the evaporator. This was then used to find the heat flow rate from the air. We also needed the mass flow rate of the air to do that. We found the mass flow rate of air from the density of air times the area of the intake pathway times the intake velocity. Again, as you see here, as we decrease the charge, decrease the amount of freon in the system, the rate of heat transfer out of the air decreased. At the evaporator, the rate of heat transfer away from the air is equal and opposite to the rate of heat transfer to the freon. So with this relationship, we could then take the heat transfer to the freon along with the enthalpy change of the freon across the evaporator in order to find the mass flow rate of freon in the system. We then use this mass flow rate along with the appropriate enthalpy changes to find the rate of heat flowing into the freon at the condenser as well as the work of the compressor. Finally, we actually find the tonnage of the system using the conversion of 1 refrigeration tons equal to 12,661 kilojoules per hour. Using heat was transferred away from the air. Was able to find these tonnages. This one looked a little high. These looked okay. But overall, everything looked pretty good. Conclusions: the system does pretty much closely follow the vapor compression refrigeration cycle, and as the charge decreased as expected, we saw a decrease in the coefficient of performance, decrease in the rates of heat transfer across the board, and decrease in the tonnage of the system. There are some sources.